up until this point, we've been very limited as to what types of triangles we could solve using trigonometry, because trigonometry is based off of the ratios that we created for a right triangle. For instance, sine of theta is equal to the opposite side over the hypotenuse. But if we don't have a right triangle, then we have no hypotenuse. And so we're not going to be able to actually use the trigonometric functions for any triangles other than right triangles. So what happens if we want to solve a triangle referred to as an oblique triangle? An oblique triangle is nothing more than a non-right triangle. In an oblique triangle like the one shown here, we don't have any right angles. This is not a right angle. This is not a right angle. And although this over here, the angle B looks like it might be, I'm going to say that it's not, and let's just say that it's 92 degrees. It's not a right triangle, and therefore we can't use trigonometry in order to solve for this particular, or solve for any of the missing sides and angles. But why don't we try to derive a formula for that by maybe dropping an altitude from the top angle in order to form a couple of right angles. Let's refer to that as the height h. Well, based on this, we now see a couple of different triangles. We see the one over on the left that I can ask something about sine of angle A, and I see a triangle over on the right where I could also ask something about sine of angle C. So even though we see that this isn't a right triangle, we could still do a little bit of work in order to find that sine of angle A is equal to the opposite side of h over the hypotenuse, which is now C. And if we look at the other triangle, the larger one on the right side, then we could see that sine of angle C is equal to its opposite side over the hypotenuse. And so that means that this is equal to h over A. Now this would require that we know what h is. Unfortunately, that would mean that we would have to find the height of each triangle in an oblique triangle. And I would prefer not to do that. So why don't we do a little bit of algebra by multiplying that c over to the other side, and we get that c times sine of angle A is the value of the height. But if you look over at this one, we also see that A times sine of angle C is equal to the height. And so since both of these are equal to the height, that must mean that both of them are equal to each other. So we know that C times sine of angle A is equal to little a times sine of angle C. And even though this isn't a right triangle, we can now erase h, and we could say that there's a relationship between angle A and its opposite side, as well as angle C and its opposite side. And so the easier way to look at this is by getting all of the A's and C's on their own side. So if I were to divide, we can divide this side by A to move it onto the other side. But then we could divide the left side by C in order to get it onto the other side as well. Which means that we actually have a relationship between these that says that sine of angle A over A is equal to sine of angle C divided by C. And what we see here is a portion of what we call the law of sines. The law of sines is what allows us to still use trigonometry in order to solve oblique triangles. But you may notice that this has nothing to do with angle B at this point. And that's because in the first one, we cut angle B in half. well, not in half. It just did. If it was isosceles, then we would have. But we cut angle B so that this and this were not angle B. So why don't we start at another angle, and maybe we could cut angle C straight down in order to form, again, two right triangles. If we do it from that perspective, then we should be able to see as well that sine of angle B is equal to, if we call that the height now, is equal to the opposite side, I'm sorry, the angle B, so that's the opposite side over the hypotenuse, because notice the hypotenuse is always opposite the 90-degree angle. So we see the sine of angle B is equal to h over a. But if we look at the other angle, we could also see that for sine of angle A, that's equal to the opposite side of h over its hypotenuse, which is B. So we also see that sine of angle A is equal to the opposite side over B. And in a very similar scenario as we did in the last formula, we could cross multiply and say that A sine B is equal to the height. But we could also see that B sine A is equal to the height. And since each of those heights are equal to each other, then that must mean that A times sine of B is equal to side B times sine of angle A. But for the same reason that we wanted to get the variables on one side, the angles and their corresponding sides, we could divide this and find out that we now see that sine of B over B is equal to sine of angle A over A. But notice how sine of angle A over A is also equal to sine of angle C over C. So we can now just set up one single law of sines that says that sine of angle A over its opposite side is equal to sine of angle B over its opposite side, which will also be equal to sine of angle C over its opposite side. And this is referred to as the law of sines. It's a formula that shows the relationship between all three of the angles and all three of the corresponding sides. Now, some textbooks like to do this or write this a little differently as well, and they just write this as the reciprocal. So you could also write this as A over sine of angle A is equal to B over sine of angle B, which is equal to side C over sine of angle C. Both of these are equivalent to each other, but the one that we're typically going to use in general would be this law of sines that relates all 6 pieces of my triangle. And part of the beauty of this formula also is that it doesn't require us to know what the height of the triangle is. The height was simply there just so that we were able to derive this formula. So let's solve a couple of triangles using the law of sines. Well, in a practical sense, in order to use the law of sines, we are only going to be dealing with 2 ratios at a time. So for instance, we need to be given, or we're only going to be dealing with, say, the ratios involving A and B, or we're going to be involving the ratios with B and C, or we would deal with the ratios involving A and C. So in either one of those 3 situations, we need to be given a full ratio if we expect to be able to use the law of sines. So what do we need to be given? So notice, in order to have a full ratio, that would imply that we would need to be given, let's say, something like angle A and side A. So once we're given that angle and its opposite side, we could virtually be given anything else. We could be given angle B, and the way that we refer to that scenario is angle, angle, side, because we're given an angle, the angle right next to it, and the next side that you see. Or if we're given angle A and side A, we could be given angle C, which you might notice is exactly the same thing. It's angle, starting with angle, angle, side. So obviously, if we're given any full ratio and any other angle, we could find the rest of the information we need. But what if we were also given perhaps another side? So instead of being given the angle and its opposite side with another angle, maybe we're given side B. At which place that would mean that we were given a side and the side right next to it, and then the angle, which is what we refer to as side-side angle. Side-side angle. Or instead of being given side B, maybe we were given side C, which is exactly the same situation, which is side, side right next to it, and then the next angle you see. So moving around the triangle, that's what we're referring to when we say side-side angle. But it turns out that we may not be given a full ratio. It's very possible that we're given something like two angles. Oh, let's say we were given two angles and that side. So notice from our formula over here that that wouldn't give us a full ratio. A full ratio meaning that I would need to know an angle and its opposite side so that I complete a full ratio. Okay. And so notice that that would imply that I would be given angle A, side B, and angle C. Now it turns out that even though I'm not given a full ratio, I could still do that one, which is angle, side, angle. Because we're given an angle, the side right next to it, and the next angle we see. And the reason why we're able to do this, even though we don't have a full ratio, is by the angle sum property for triangles. We know that the sum of all the angles adds up to 180 degrees. So if we're already given two angles, then we automatically can find the third by subtracting from 180. And if we subtract A and C from angle B, or from 180, we get angle B, and notice that at that point, we would then have a full ratio. So the point of this is we need to have a full ratio regardless of what the situation is. Now, there are a couple of situations where we cannot use the law of sines. There are a few instances where we actually cannot use the law of sines if we happen to be given certain information. So let me start off by just saying, what if we're given all three angles? Well, if we're given angle, 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 then we definitely cannot find the missing sides for a couple of reasons. One, I would have the angle, and the angle, but no full ratio. And with no information about any sides, we have no idea how big this is. And so notice for this one, this is impossible to solve if we're given all three angles, because we have no scale about how big or small the triangle is without being given at least one side. So what if we happen to be given all three sides? Side A, side B, and side C. Well, now notice in our formula, that would mean that I would have all of the denominators. But if I have no angle at all, then I have no full ratio. And so if I'm given side, 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 then I am not able to find or use the law of sines in order to solve for the missing information. But there's one other scenario as well that we didn't handle with either of these. And that's, what if we happen to be given two sides, like side C and side B? If we're going to be able to solve for this, we would have to be given either angle B or angle C so that I could complete a full ratio. But what if I happen to be given the angle in between the two sides? Then I would have this angle right over here, which would mean I wouldn't have a full ratio filled in. And because I'm not given two angles, I can't find the third angle. So we refer to that as side, angle, side. And so in those two situations, side, 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 given all three sides, or side, angle, side, where we're given an angle in between two other sides, we're not able to use the law of sines. So in order to solve for triangles where we're given that information, we need another formula that we'll derive later that's referred to as the law of cosines. But at this point, the easiest way to determine when you can use the law of sines and when you can't is whether or not you have a full ratio to be able to solve. So let's take a look at an example. Now in this situation, we're given two angles and a side. But the thing that I'm recognizing first is that I know that I'm able to solve this because I have an angle and I have its own opposite side, which means I know that I'm going to be able to fill in an entire ratio. So that means that I could start by writing my law of sines, saying that sine of angle A divided by its opposite side is equal to sine of angle B, which again I also know is 81.8 degrees, over its opposite side. But since I know the opposite side of 32 degrees is 42.9, notice that the law of sines only has one single unknown. And so B is what we're trying to solve for. So we could cross multiply, giving me that B times sine of 32.0 degrees is equal to 42.9 times sine of 81.8 degrees. And so at this point, and if I want to solve for B, B is equal to the right side, which is still 42.9 times sine of 81.8 degrees, divided by sine of 32.0 degrees. So just by using the formula that we derived earlier, we now can find what side B is by punching that into our calculator and finding out that side B is equal to approximately 80.1 centimeters. All right, which is great. So now we know side B, we know side A, and we know the angles of A and B. So the only things we don't know are angle C and side C. Well, if we're going to use the law of sines, then that would mean that we would have to know something about sine of angle C or the side C, which I don't know either one of those. So before we can do anything, we're going to have to find side or angle C. We should remember that C is equal to 180 degrees minus the sum of the other two angles. So since I already know these angles are 32.0 degrees and 81.8 degrees, the sum of all three angles has to be 180 degrees, and therefore we know angle C. Angle C, use our calculator here, and that's going to give us 66.2 degrees. Great, so now we know all three angles. We know angle A, angle B, and angle C. And so the only thing we don't know is side C. So now we can fill in the law of sines, sine of 66.2 degrees over C is equal to, and now I get to use either one of the two formulas at the beginning. I could use the ratio involving A's, or I could use the ratio involving B's. Now notice, I know what B is. We just found B. So I could plug that in. But when you have a choice, and you always do, you should always use the law of sines involving the two quantities that were given at the beginning of the problem. Because 80.1 is an approximation. I rounded that, which means if I use an approximation to approximate something else, it's going to be an even worse approximation. So that's why we're going to set this equal to sine of 32.0 degrees divided by 42.9. And now if we cross multiply, we get C times sine of 320 or 32.0 degrees is equal to 42.9 times sine of 66.2 degrees, which means that C can be solved by just dividing both sides by sine of 32.0 degrees. And so you might notice in finding B and in finding C, the processes were almost identical. Notice the only difference between the two results here is the fact that this one said sine of 81.8 degrees, while this one says sine of 66.2. And so when we use our calculator to solve, we finally get that C is approximately equal to 74.1 centimeters. And so this is pretty cool because now, even though we are not dealing with a right triangle, notice that none of the angles were 90 degrees, we're still able to use the trigonometric functions to solve for the missing information. The only difference is that now we can't just use the trigonometric function as it is, we have to use the formula involving all of the angles and all of the sides. Taking a look at an example now, we can see that in a situation or an application problem, the most important task is to draw an accurate diagram. So let's start by reading it carefully and trying to come up with a visual of what's going on. So two ranger stations are on an east-west line 100 miles apart. Well, the first thing I would start with then is just to realize that an east-west line would look something like this. And so we know that there's going to be one ranger station, we'll call that the one on the west, and another ranger station, we'll call that the one on the east. And we should realize that that is 110 miles apart. Okay, well from there, it says that a forest fire is located on a bearing of north 42 degrees east from the western station. So there's a fire somewhere up here in the hills, okay? Now the way that we know where it is by pointing north, okay, pointing towards the north, and turning 42 degrees towards the east. So I'm going to draw, here's halfway, so 42 degrees is going to be somewhere about right here. So I know that the fire is going to be somewhere along that line right there. But then it says that from station A, it's at a bearing of north 15 degrees east. So that means, again, from north, we're going to turn 14 degrees towards the east. Okay. Oh, from the western station A and a bearing of north 15 degrees from the station A. I realized we should have labeled these differently because I drew this incorrectly. Okay, so we've got, let's just say angle A, or side A and side B. Okay, so notice that this one is north 42 degrees towards the east. Okay, because it said from the western station at A, and a bearing of north 15 degrees east from the eastern station at B. So when I take 15 degrees east, that's a pretty shallow angle. So when I go 15 degrees towards the east, it's going to be somewhere over here. Now I can see that eventually these are going to cross, but it's going to be quite a ways up there. And so let's move this down. So now we know that the fire is going to be somewhere in this general vicinity right here. Okay, and let's call that angle F for the fire. And so now to go back to our diagram, we need to fill in some angles. So we were told that we went north and turned 42 degrees towards the east, which is why this is a 42-degree angle. And I also was told that this started at north and turned 15 degrees towards the east. So this is a 15-degree angle. And now we're trying to use all of this information in this triangle to somehow find how far away the distance, or how far away it actually is. Now, how do we know this? It says to the nearest 10 miles, how far is the fire from the western station? The western station is over here. So although it looks from our diagram that it's actually closer from angle B, perhaps for this fire station or this ranger station that's over at A, it's an easier access to get to the fire, even though it's further away. And this is perfect for some wildfires that happen to be going on in California right now. And so notice that what we're trying to do here is find this side. And I'm going to call this little b just because of the fact that I'm given angle B. All right, well, if I'm going to be able to solve for side B, then I should probably try to set up the law of sines to look like sine of angle B over side B is equal to, and now I have to realize that the only other information I'm given in this triangle is this 110 miles, which is the opposite side of F. So that must mean that the other ratio I need to set up is sine of angle F over 110 miles. Now keep in mind, all I'm trying to find is side B. So it's not one of the scenarios where I'm trying to solve the entire triangle. I just have to solve for the quantities that I need in my problem. Slight issue in our diagram because we don't have any of the angles in our triangle. We don't know this angle up top. We don't know this angle right here. And we don't know this whole angle down here. So we don't know any of the three angles in our triangle. So that's why we're going to have to do a little bit of logic here in order to use the fact that in a compass between north, south, east, and west, that these are all 90-degree angles. Which means that if this part of the angle here is 42 degrees, then the angle down here is going to be its complementary angle of 48 degrees. I also know that this piece right here is a right angle. And so this whole angle is going to be the right angle plus the extra 15 degrees, which gives me an angle of 105 degrees. So that's great because at least we could come up here and fill in for sine of angle B. We could fill in our 105-degree angle. And we're trying to solve for side B. But if we're going to do that, we also are going to need to know what angle F is going to be. But keep in mind that if I've got two angles in the triangle here, that I could find the third angle by just subtracting from 180 degrees. So we could find out that angle F is equal to 180 degrees minus the sum of 105 degrees and 48 degrees. So that gives a total of 153 degrees. So when I take that away from 180, that gives me a total of 27 degrees. So now we know that the angle formed right at the fire, looking back to both of the ranger stations, is an angle of 27 degrees, which means we can come up here, fill in angle F, and the only unknown is the side that we need. So cross multiply, that gives me that B times sine of 27 degrees is equal to 110 miles times sine of 105 degrees. So in order to find B, we just simply take 110 times sine of 105, sine of 105 degrees, and we divide by sine of 27 degrees. And by working all of that out, we find out that B is approximately, using our calculator, 234 miles. So we now know that the distance to the forest fire from the ranger station in the west is 234 miles away. And that was simply by using the law of sines to solve for a missing side by being given certain information about the distance between the ranger stations. In addition to finding missing sides and missing angles within an oblique triangle, we're also able to find the area of an oblique triangle, except that we've got a slight issue, because if you take a look at the formula for the area of a triangle, it's 1/2 the base times the height. Now, if we're given a base, that would be great. The problem is we're not going to have the height typically for an oblique triangle. But why don't we go ahead and use the same proof that we did for the law of sines, and just pretend for a minute that we do have A, or we do have the height rather. And so if we have the height, then we could set up a couple of different relationships, right? We could see that that sine of angle A is equal to H over C. Or we could see that sine of angle C is equal to H over A. So we could indirectly use the information about the angles and sides of our triangle by realizing that the height is actually equal to C times sine of angle A. Or if we look at it over here, we could see that the height is equal to A times sine of angle C. So in either one of these situations, we would now know what the height is by using either one of the information in our triangle here. So we could go back up to our formula and recognize that the area is equal to 1/2 the base of B times C sine of A. Or I could write it as 1/2 the base, which in this diagram is B, times A sine of C. And so in general, even if we're not given the height of our triangle, we still have some formulas to find area. And the area is either 1/2 side A times side B times sine of the angle between them, or it's equal to 1/2 side B side C times sine of the angle between them. So you could either say A and B and then use the angle in between, or you could use C and B along with the angle in between. But if we were to draw a different height, we could also use side C and side A along with the angle in between here. So we have a third formula, which is 1/2 A times C times sine of the angle between them. So what this allows us to do is use a different formula to find the area of a triangle, even when we don't know what the value of the height is. All we need to know is some information regarding the triangle itself.